Okay. Now complexation. Okay, so let's say ammonia now. Instead of using a weak acid, now it's just a molecule, complexation molecule, such as ammonia, because of the unbonded electron pair. So coordination chemistry will teach you the reasons behind. So here we're just concerned with calculation. Okay, so silver and ammonia mix, you're going to have in a mixture, okay, going to have the complex and the free silver. So this is your mass balance equation, right? Okay, then here, the complexation stops at this chemical formula. It will not continue with ammonia 3 or ammonia 4 with silver. Then how do you know that? Well, the table, when you read the formation, K formation table, it starts with this chemical formula. So you know how many Kf. So there will be only 2 Kf. So this one is Kf1, this one is Kf2. Then you don't have Kf3, so on and so forth. So that you know, okay, and it stops to that form. So important, be sure you know how to read the table. Otherwise, you may continue to write, ammonium 3, 4, so on and so forth. When do I stop, So now you know when you should stop, referring to the table. Okay, so mass balance. So if you have an analytical concentration of silver, then they will, mixture is going to distribute among the 3 possible species, more or less. Any question with that? Okay, so now is some definition. Beta 2 prime, or some book called it alpha 2 prime. Now what is the 2? The 2 meaning this 2, with 2 ligand or complexing agent attached. So with 2, then it's beta 2. Prime is defined as the fraction. So fraction of this to the total. So that is the definition. So the detail is here, the second complex. If this is what you are interested in, learning is fraction to the total. Okay, so this is the definition, the longer definition. Okay, so next we're going to derive an expression. Okay, this fraction for a particular species versus, as you know, how much ammonia at equilibrium that you're going to use. So this is a quantity you use to lead you to know what will be at equilibrium, the free concentration. So experimentally, you can design that, simply use concentrations. Okay, by simply knowing this quantity and of course the Kf values, okay, with the tool knowledge, because silver is going to be limiting such as a small quantity compared with that, so it's often simply that you know this and that, and this is specific for the particular complexation. Once you have this involved, then you know the system is between silver and ammonia. Okay, so the derivation is like this. So you are interested in the beta 2 fraction. So the beta 2 fraction is right here, up here. Then algebraically, you just divide all the parameters by the species of interest. Okay, by the species of interest, which is the 2 complex. Okay, so the top one now divided by itself, of course, is equal to 1. Okay, now the bottom one, the silver ion divided by that, 2, then you will need to have a definition, the KF definition. Okay, then the first complex divided by the second complex. Then here, the second complex divided by itself, then reduced to 1. Okay, so instead of writing silver, we are deriving a relationship to ammonia and Kf only. So now you need to go back to the equilibrium expressions, Kf1 and Kf2. Okay, so you will have intermediate for Kf1 product. Okay, so this is going to be equivalent to the reciprocal of this 2 multiplied by that 2. So we did this kind of derivation earlier. So review a previous lecture. So you know what that is. And here, similarly, you know, this is from the first one, add another ammonia to get to the second one. Okay, remember that particular reaction. So this one add an ammonia to form this product. So that reaction is Kf2, specific Kf2. So the reciprocal of this multiplied that is equal to this whole deal. Okay, so remember to practice the transformation at home when you review the topic 10 plus 1. So now you see that the fraction relationship to just the K values and ammonia equilibrium concentration. Okay? So for beta 2, you don't like the reciprocal deal, then you can flip it normally, then it looks like that. So this has practical application. So if you do an experiment between silver and ammonia, then you know this will help you how to design your procedure. So similarly, if you are interested in the first complex, the fraction to the total, then you're going to do a similar derivation. Then it's going to be Kf1 multiplied by ammonia, okay, like this. So this is your relationship. So if you want to know how much silver ion uncomplex in a mixture, then is equal to this. Well, you just go through the derivation, you know, for the species of interest divided by itself equal to 1, and so on and so forth. And you end up with that. Okay, so on an exam problem, I might ask you to derive, you know, beta naught fraction, you know, for relationship to the Kf and ammonia concentration. Okay.
You go back.
Okay. Oh, sorry.
You just press up. Yeah, it's this one. It's this.
Where? Bottom.
No, it's this like that.
Do it just like this. Okay, when I press the button, will it go?
Oh no, this was just a slide that
Well,
Yeah.